Okay, so let's get started again. So we have a slot here for a discussion on computational methods, and the way I thought we would get started, and maybe actually the way we will finish, given the limited time, um, is there's a number of people here who have a lot of involvement with various public codes that are quite widely used in the planet formation field, mostly on, particularly in the hydro MHD kind of area. So I thought get started by just asking a few people maybe to say a few words about the capabilities of different codes we have, and perhaps in some cases the sort of plans that we have for developing those codes and adding new capabilities. And the sort of thought here is that this might be both maybe useful to, not everyone here is familiar with every code, so that might be useful for people in a direct basis. And then on a sort of longer term basis, it might help spur some discussion maybe over lunch and later over what new capabilities we would like to develop in the future that would be important for some of the problems we've been discussing and will be discussing later. And I'd also be interested in a discussion with people about what CCA and the Flatiron Institute could do perhaps in helping to facilitate that, because small workshops that are more focused on code development is something also that we're quite keen on doing here. So a few people sent me some slides, so we'll go through this in a sort of semi-random order. So maybe we'll start with Fargo 3D, and Paolo can say a little bit about that.
It's a code that I started to develop during my PhD with Frederick Marcet. So this is a completely rewritten code. So many people know the code Fargo code. This is the version that was written by Frederick, and we decided to start a new project several years ago. And the main goal of this code was to have a versatile GPU code to simulate protoplanetary disks. The results that we have now a CPU and GPU multi-fluid MHD code is multi-fluid since the beginning of this year. The goal, so how the code works. So the code is a high-performance computing code. It can work on shared or distributed memory clusters, CPUs or GPUs. So you can choose, if you don't have GPUs in your cluster, you can use CPUs. The memory, so what is complicated usually for CUDA is to manage the memory, so to transfer memory from what is called host and device. And we did we developed a framework to avoid this complication, so we have some sort of automatic memory management to deal with this. The important part of the code is that we don't need to know about GPU computing to extend or to develop new source code, because we have developed a parser that translates CPU functions to GPU ones. So in this way, we know that all the code is homogeneous. So all the routines that works on the CPU also works on the GPU. The codes allows you to use different geometries. It's Cartesian, cylindrical, spherical, so you can also do 1, 2, or 3D simulations. It's important to realize that you don't need to have uniform meshes in the code, so they are structured, so the meshes are formed by the Cartesian product of 3 directions, x, y, and z, for example. So you can, for example, in this way, refine a cylindrical mesh in radius. One important limitation that we only have uniform meshes in azimuth so far. There are different modules that were developed to solve different problems during the years. We have viscosity, different energies of equations, or different equation states. We have embodied solvers inside the code, ideal MHD, orbital advections to speed up the calculations. So that's why the code is called Fargo. We also added recently the possibility of simulating multiple fluids with the aim of simulating dust, but you can also simulate different gas fluids. We also have some, all these features are public, but we also have some non-public features that may become public in the future. Like dynamical remapping of meshes. So we can, for example, track a planet while it migrates, which is very important if we want to simulate long-term planet migration. We also have radiative transfer modules using flux limited diffusion. This is a simple radiative transfer module. We also included non-ideal MHD. That was part of the work of Leonardo Krapp. He implemented this. We also have nested meshes. People in Mexico are working in this. David Velasco and Frederic Masset are mainly involved in this project. And we also have some recent self-gravity module under development. There is a master student working in Copenhagen right now trying to implement this module. What is important about the code is publicly available. This is you can see there the license that we use for the code. We have a public repository since January this year. We also have extensive documentation for the code, so most users should. I think they could start to use the code just by reading the documentation. The main developers of the public version of the original public version was, of course, me and Frederic Masset, but we are also open to contributors, so to include new features in the public version. The most recent one was developed by Leonardo Krapp, was a multi-fluid version. And we also have a lot of input so we have a Google group, and we have a lot of input from the people that uses the code. It's very important because in this way, it's the only way in which we can fix the different bugs that we have. The most important property of the code. This is a code of the Zeus family. It's fluid dynamics using finite differences, upwind, and dimensional split methods. It's important to realize that mass and momentum are strictly conserved because of the framework that we use to solve the equations. We cannot ensure conservation of energy in the code, so energy is not solved in a conservative way. But if we work in isothermal setup, for example, as usually in protoplanar, for example, planet migration, we can ensure that the shock jump conditions are satisfied. So the codes can reproduce these dynamics very well. And yes, if you have some questions, please ask me. You can also ask Leo. And yes, that's more or less what I have to say. Thank you.
Thank you. And I think next we have Phantom, and Giuseppe agreed to say a little bit about that.
Phantom is an SPH code, essentially it's meshless. There is no mesh, and it's in terms of the gas dynamics, it's got the really the most advanced SPH algorithms. So the formulation is fully conservative. And it conserves everything: mass, linear momentum, angular momentum, and energy in principle. It's got some of the most advanced switches for limiting artificial viscosity. The Cullen and Dennen is the most recent one, and you can choose very freely. It's a modular code, so you can easily choose the kernel function that you want to use, the kind of switches that you want to use, etc. Obviously, there is self-gravity. And Daniel Price, who's the main developer of the code, has also worked a lot on including MHD. And then we have dust. And there are three possible ways in which you can treat the dust in the code. There is the one that we call two-fluid, which is appropriate for large Stokes number, so relatively uncoupled dust, and where gas and dust are treated as separate particles. And then there is the other regime that we call one fluid, which is where the gas and the dust are treated as a mixture, which is appropriate for small Stokes number. And then recently we also have the multigrain dust treated as a mixture. It's also freely available. There is a Git repository up there, and there is some development taking place now. The most important ones are probably the doing multigrain simulations for large particles, because right now the multigrain is only available for the coupled case. And then there is some development, like in terms of coupling Phantom with MC-FOST, so that we can have live radiative, well, not radiative transfer, yes, Monte Carlo ready to transfer for irradiated disks. Maybe I have another slide, do I? Yeah. So if I want to summarize the advantages and disadvantages of using Phantom, well, it's an SPH code, so it's got all the advantages and the disadvantages of an SPH code. The advantages is the ability to treat complex 3D geometries. So since we don't have a mesh, we can easily treat warps, flybys, shadowing effects, binaries, all these kind of complicated geometries that are now being observed in many systems. These are very easy to simulate with SPH, and it's been extensively tested and validated. It's been in around since 10 years now. And it's actually tested every night on a suite of standard problems. So that we know is not broken, even with all the development. The disadvantages is that it's SPH, so when you have low density, you have a lot of dissipation, which might be a problem, for example, if you want to treat a gap. Because by definition in the gap the density is low, the resolution becomes high, and you have more dissipation. It's well known that the viscosity scales with resolution, and actually, if you calibrate that, turns out that if you use 1 million particles, which is the number of particles that people usually use these days, basically you reach a viscosity down to 0.01 in terms of alpha, not much below that. This means essentially that if you want to have low viscosity disk, you need to have many more particles than 1 million. Okay, so if you want to and it scales with the cubic root of it. So basically, if you want to go down to 10 to the minus 3, then you need 1 billion particles. Okay, so this might become hard to do. And for the dust, well, the limitation of the dust module, I think, is inherent in all the any other dust treatment. If you want to use a mixture, then you need a Stokes number to be smaller than h over h, where small h is the resolution length, and big H is the thickness, which means that if you increase your resolution, small h becomes small, and this means that the mixture can only be applied to very tightly coupled grains. And in the two-fluid case, so when you have a large Stokes number, there is this problem that particles might, dust particles might get stuck below the resolution length, which can cause some spurious effect. But I think these features here are these limitations are inherent in all the dust treatment in all the codes. And I personally think this is the SPH code that should be used for this simulation. This has been initially developed with an it's a multi-purpose code, but it's been developed with an eye on protostellar on disks in general. So that is what it was meant to do. So so in terms of SPH code, I think this is the one that one should use. Then the question is whether you want to use SPH or not.
Thank you. And now maybe Jim can say something about Athena.
Okay, so I'll be very, very brief. There is an older version of Athena still available, Athena 4.2, which has got a lot of stuff in it that's been used extensively for prototype disks. So that's certainly available for anybody to download and use. There is a new version, Athena++, primarily rewritten because of the need to include adaptive mesh refinement using a block-based strategy that was going to be very difficult to add to the old version. Also general coordinate systems, allowing us to do GR and other things. So Athena++ really is more of a framework than an MHD code. A framework for handling arbitrary meshes, AMR, and task-based execution. And once you have that mesh, then you can add whatever you want to it. There's an MHD solver. There's a relativistic MHD solver, may not be useful here. There's self-gravity. There's a new dust module being written by Chao-Chin Yang and Zhao Zhu, which builds on the solver that Zhuoning Bai wrote for the old version of Athena 4.2. There's also a rate of transfer solver, which incorporates both flexible diffusion but also full transport methods. And I personally think that exploring rate of transfer effects is a very important area. So these full transport methods are something to be explored. There's basically all the features of Athena 4.2 will eventually get into Athena++ into the public version, but it may take a little while. The public version of Athena++ only has the MHD solvers basically at the moment. There is also a new GPU version that was written by somebody who downloaded the public version and adopted this Crocos library. Got some interesting results on that, so we're also looking at pulling those back upstream into the development version. So if you're interested in the GPU version, there's a separate URL for that. It's called K-Athena or Kathena. So if you're interested in trying that out as well. Okay.
Thank you. And then I think Keaton, has a slide in a moment on Daedalus.
Okay, so Daedalus is a open source Python-based PDE solver, and it's actually a general PDE solver, not specific to hydrodynamics. So it's a framework for implementing sparse Fourier and global polynomial spectral methods. So the main limitations are the ones that are kind of inherent to global spectral methods. So it only really works for simple geometries, but that gives you things like boxes and annuli and disks and spheres. And it has essentially uniform resolution at all points in the domain. The big advantage of spectral methods is that they give you exponentially converging solutions for exponentially converging accuracy for smooth solutions. So typically, if you're formulating a hydrodynamics problem, you need to add explicit viscosity and diffusivities, but then the spectral method solves that regularized problem very accurately with essentially like no numerical dissipation. So really the point of the framework though is the flexible equation entry. So we actually don't implement any equations internally. We implement a parsing framework that lets you just symbolically specify systems of PDEs that get turned into this sparse spectral system. So that makes it really easy to add new physics and different models. So it's very easy to switch between incompressible hydro, fully compressible hydro, add magnetic fields, do multiple fluids, those sorts of things. So you have to regularize them with viscosity. So you put in enough viscosity so that the shock is regularized on the scale of the grid, and then that's it.
Okay. And then I think Vlad has some slides on pencil.
So yeah, the pencil code is a finite difference code. It's non-conservative, but it relies on high accuracy to achieve, right, the conservation that you need. So the high order is shown there in the left-hand side. This is actually something that I got from Wikipedia. You can see the coefficients there. If you want to have high order, you check there which are the coefficients that would give you the desired accuracy. In the pencil code case, we use 6th order accuracy in the spatial derivatives and 3rd order in time. So on the right hand side, you have there the accuracy of the first and second derivative. The full line is what you would get with no discretization. That's what spectral methods do. The 6th order, that's the big dashed line. So you see that you are accurate half of the way to the Nyquist frequency, or 2/3 of the way there. And the bottom plots show if you have an Alfvén wave, so you do an advection of an Alfvén wave for one cycle, the accuracy that you get. So already at 8 points, you see that you may not get the phase right, but the amplitude did not go down. So that's a feature of the 3rd order accuracy in time. The other plot, the 16 points, you see that you get both the amplitude right and the phase also. um, already at this low resolution. Can we change the slide? Right. So to regularize it, a high order will tend to accumulate energy near the grid. So the upper plot show a field, and then you do the advection of this field, and then see how much dissipation you get. The middle plot shows the power that you would get for Laplacian dissipation, which is n equal 1, and hyper that we use, that's the blue line. So you see the shape didn't change much, right? The lower plot shows the power that you get from these two dissipations. The idea is that you near the grid you get the same dissipation you would get from Laplacian, but then at the integral scales of the flow, like near k equal 1, the blue line, you get much less power. So in there you are close to inviscid. The next one. So the checklist, what the code has, it's grid-based. It has particles, MHD, either ideal or non-ideal. The dust can be implemented either by multifluid or superparticles. There is a module for chemistry. I haven't used that module much, but other people have used. Radiative transfer, it's a multi-use code, right? The chemistry actually comes because there are some people in the code that use that in industry. Industry likes it because that's the only free code that does that, so they use that. RT, yeah. People that use that for the sun like to use, short and long characteristic. The code has that. In disks, we use more FLLD. You can do that either Cartesian, cylindrical, or spherical. It has been implemented both for the sharing box and global disks. Self-gravity, yeah, we have that for the sharing box, Cartesian, global, and for 2D in polar coordinates, not yet for 3D polar. The grids can be non-uniform. We don't have yet nested meshes. And Fargo, yeah, we implemented that recently, so we can try to put the next one. So one of the points of the pencil code is the way that it does MHD, right? It does not solve for the field, but for the potential. That makes it easy to use Fargo because you can expand the electromotive force into two terms, and one of these terms, the first one in the right hand side, is an advection term. So you can use that to do the algorithm of Fargo as you would do for the other quantities too. The next slide. So that's the solution that you get there. So the middle plot show the orbital advection. I mean, with the orbital advection and the standard without it. The difference that you get is of the order of 10 to the minus 6. So.
Thank you. So we have a few minutes left. So I think at this point I'd just like to invite anyone who either wants to say something else about other codes or more general comments.
This in green yet? There was two mentions here about dealing with hybrid computer architectures, things with accelerators and CPU. And the last thing I was at was a European Union exascale workshop last week. And it's pretty clear that if we want to do grand challenge kind of big simulations on these upcoming machines, that's the kind of architecture we need to be targeting. Whereas most of what we've talked about here doesn't support it in the main distribution, at least, or is still coming up. So, from the people who are in the core of these projects, what are the right ways to do this to get something that's will live for 10 years on lots of different architectures and is worth maintaining? And where's that going to go?
Mordecai?
Up on that, the Insight DOE computers, which are the biggest publicly available US computers, are also hybrid architectures, and they're also pretty much only going to give time to people who can run on GPU plus CPU. I also have a code comment, but yeah, if someone else wants to jump in on this topic first.
Anyone want to say anything about GPUs?
Comment that for hybrid codes, there is a code out there called Gamer, which is a GPU CPU code. It's developed in NTU in Taiwan now. So if you're interested, I think there are method papers on the archive now. You can also, if you're interested, you can also talk to me. I know the author of the code. So, Gamer.
Well, actually, if specific, so yeah, there's a bunch of little things out there, but what's the is there a way of developing these? A set of, there was a mention of the Cocos library. Pablo has this little a script that will translate kernels of a particular format into CUDA. But one of the problems with all these is maintainability in the long term. And what we're actually going to use to handle programming these complicated architectures. And it would really help if I knew or we knew where the critical mass will be, as which technology is going to be the one that emerges as useful.
Simeon, do you want to, or Jim?
Simple answer to that question, obviously. The entire high performance community is interested in the answer to that question, and no one knows the answer right now. I personally, for a long time, have not been a big fan of GPU computing. I'll just be completely honest, because it requires writing in a special language, CUDA, to get really good performance, and then your code's not portable. I think if you just optimize for CPUs, you can do pretty well, and so that's what we spent our time doing. However, it's becoming clear that these big machines are going mostly towards GPUs. There will be an Intel-based machine, and Intel has not even announced how you will program that machine yet. And there will be an NVIDIA GPU-based machine, which will probably run CUDA. Nowadays, however, program portability is becoming ever more important. And so I think recently you begin to see libraries emerging like Cocos, which allow you to, it'll automatically translate the source code into executable for either kind of machines, or into a language that those machines will compile easily. So it automatically translates your code into CUDA, or it'll leave it as Intel, it'll be compilable by the GNU library and run on CPUs if you want. So I find that much more attractive, and so I think that's one possible way forward. Whether Cocos will survive the next 10 years, I don't know. It's being supported by one of the national labs. All of the Insight machines are being bought by the national labs. I would imagine that they're going to support the Cocos library. Will the other vendors come up with good programming models? Hard to say. There are the various open source tools like OpenACC, OpenCL, but they're not a solution that requires the vendor to implement a compiler that will use those and optimize them. And right now, the vendors have not been very good at doing that. So it's still very much an open landscape. But of course, I think everyone has to be aware of where the trends are going, and that using GPUs is attractive. I would say that our strategy to moment has been worthwhile because this new Cathena is actually getting as good, a little bit better performance than Gamer, which is a very nice, specifically written code, MHD code for NVIDIA GPUs, written in CUDA, so it's non-portable, but it's really nice code. This Cathena does better than Gamer, and so for 1 Volta GPU, it runs about 5 times faster than 1 Intel CPU, which is about the ratio you should be getting based on the so that's why GPUs are about 5 times faster, but because all the big machines are going to go towards GPUs, it's probably going to be the largest hardware investments will be in GPUs in the future. So something to be aware of. I don't know if it. I'm sure others have other opinions or insights that they could also provide.
You want to say anything about like what Evan Schneider's been working on, Chola?
So she has another really nice, special purpose CUDA code for doing. It works only on a Cartesian regular mesh for hydrodynamics. So this is a good example though of the challenge. In order for her to extend that code to MHD, requires her to implement all of this new into all the MHD algorithm into CUDA, and so that's a lot of work to port existing CPU codes and GPU. So she and I are exploring the use of Cocos in Athena++ developmental version, because it's probably a lot easier for us to extend Athena++ to Cocos than it is for her to implement MHD into Choya. That's a big task. So this is, again, having to rewrite your code for every architecture available is just not maintainable by a small community like this. And so having portable tools is really crucial. And I've always been a big fan of portability, because otherwise, if that vendor goes away or you can't get access to that machine, you're stuck about what you're going to do. So having portability is really, really important, I think, for a small community which doesn't know where the hardware is going in the future.
So I just wanted to mention a code that hasn't had a lot of use, or a code framework, I should say, that hasn't had a lot of use in this community yet, but some, which is the Amuse framework, Astrophysical Multipurpose Software Environment, that Simon Portuguese Svart has been developing. And this came out of the N-body community and is intended to link many codes together on effectively a time-step-by-time-step basis. Recently, working with Joshua Wall and Steve McMillan, we've included Flash into the Amuse framework. So carrying the full MHD structure of Flash into Muse, and this allows coupling of N-body with Flash. And for example, you can run N-body codes that will access GPUs like PH4 that Steve McMillan developed, and then include that with all the other bits in the Amuse framework. And this particularly came to my mind when Jake Simon was discussing that transition from a big gas dynamic simulation into N-body. This would allow you to take a direct N accelerated or a tree-based N-body a code, and directly run it with the hydro. So that's something that people might want to keep on the radar.
Jonathan?
So along the lines of advertising a different code, I just thought I'd mention the Gizmo code because it's very flexible for geometries and has some advantages over SPH. So basically what it does is it's similar to SPH, but it also calculates the fluxes between particles or mesh or whatever you want to call it. So it can be more accurate in some cases. It's public, very easy to use, and has a lot of different options for different modules and things, different types of diffusion, MHD. I think it can even do like hard body collisions via solid equations of states and all sorts of things. So just worth checking out if people are interested.
Okay, well, I think it's pretty much come up to lunchtime, so we thank everyone for contributing here, and we can continue the discussion over lunch.